On March 31, 2026, the architectural vault of a frontier AI company cracked open, giving the public its first comprehensive look at the internal nervous system of a production-grade autonomous agent. The exposure was not the result of a targeted intrusion. Anthropic pushed version 2.1.88 of its Claude Code command line tool to the NPM registry. Due to an omission in the deployment manifest, this routine update included a 59.8 megabyte JavaScript source map file. Source maps are debugging artifacts designed to link minified production software back to readable code. In this instance, the file provided a direct URL to an unsecured cloud storage bucket, allowing anyone to download and reconstruct over 500,000 lines of proprietary TypeScript. Forensic analysis confirmed no model weights, no training data, or sensitive customer credentials were exposed. What was exposed is the complete source code for Claude Code's agentic harness that wraps around the underlying foundational model, governs its memory, and equips it with tools to interact with local file systems. This codebase indicates that the frontier of artificial intelligence development has shifted. Raw model capabilities now rely on the engineering of these complex harnesses to achieve real-world utility in developer environments. While a simple API wrapper can handle a single file, it lacks the mechanisms to navigate dependency graphs, manage long-term state, or handle tool feedback. Without a specialized harness to manage these interactions, a model loses the context necessary to maintain coherence across a complex codebase. The leaked codebase reveals dozens of compile-time feature flags. These flags allow developers to embed fully built capabilities directly into the software while physically compiling them out of the public release. The codebase branches into two paths. Flags like Kairos and Ultraplan reveal Anthropic testing autonomous behaviors in shadow mode. Notice the separation. A lightweight local terminal is entirely decoupled from a dense, privileged remote cloud runtime. This is the bridge pattern. This decoupling allows local users to oversee and approve execution plans, while the heavy, privileged reasoning is isolated safely within secure cloud containers. This decoupled architecture enables features like Ultraplan. Ultraplan offloads complex reasoning tasks to a remote cloud instance. The remote model can spend up to 30 minutes developing a strategy before a unique Sentinel value teleports the approved plan back to the user's local terminal for execution. High-value operations require deep context and extensive planning. To achieve this, agentic systems are transitioning from instant streaming text generation to asynchronous, long-horizon job execution. Traditional LLM interfaces operate as stateless chat loops, where each session ends as soon as a response is generated. The leaked harness utilizes a stateful session architecture designed for persistence. Coordinator mode is a multi-agent orchestration pattern. A primary agent spawns parallel worker subagents to handle specific tasks simultaneously. These worker nodes process their data packets in strict isolation. By enforcing explicit message contracts, the harness prevents subagent context from contaminating the main thread's reasoning. The code also contains references to Kairos, representing a shift toward persistent background daemons. This background automation is tied to specific environmental triggers. If the user's terminal loses focus, or if the system detects 24 hours of inactivity, the daemon initiates asynchronous workflows. During these idle periods, Kairos executes a process called AutoDream, which performs nightly memory consolidation. A forked sub-agent reviews the daily session transcripts, resolves logical contradictions, and updates a verified index of project facts. By running as a background daemon, the agent can monitor GitHub events and execute memory consolidation while the user is away. The system continuously maintains its own understanding of the repository, rather than requiring the user to reread or manually summarize past actions. To safely run high-agency tools, the harness implements a command-by-command architecture. Every one of the agent's 40-plus discrete tools is individually permission-gated. See how a compound shell command is evaluated. The harness splits the command into separate execution blocks, forcing each through its own strict validation gate. If one block hits a red deny filter, it instantly halts the entire sequence. The deny list always wins. Alongside these hard rules, the code reveals a YOLO classifier. This is a distinct, lightweight machine learning permission system operating independently of the primary reasoning model. The classifier rapidly analyzes conversation transcripts to automatically approve known, safe actions. It acts as a fast pass layer, preventing the system from blocking the interactive loop or interrupting the user for routine approvals. The codebase also contains an undercover mode. When active, this module instructs the model to hide internal codenames and strip AI attribution from any generated open-source commits. Execution safety is managed here not through prompt engineering, but through rigid middleware that evaluates the runtime context before a single line of code touches the local system. The value of this leak lies in applying these production-grade architectures to develop custom AI tools. Long-running agents face a specific technical constraint: context entropy. As conversational transcripts expand, the reasoning quality of the underlying LLM degrades. This funnel diagram maps the four-stage context compaction pipeline: budget, microcompact, collapse, and autocompact. Read-heavy tools bypass the first layer, while conversational blocks face strict filtering. The middle layers aggressively prune older data based on recency, dissolving it into compressed metadata. The final autocompact stage uses a secondary prompt. It summarizes the remaining conversational history into a dense, synthetic context for the model to reference. However, this compaction pipeline creates a security vulnerability known as compaction laundering. If an attacker injects malicious instructions into a file, those instructions can survive the summarization process and persist in memory as trusted user directives. Mastering context pressure and the vulnerabilities it creates during compaction is the primary technical hurdle in building agents capable of operating indefinitely without human intervention. To maintain a pristine context window, the agent relies on a strict write discipline. The core rule of this discipline is that the agent may only update its internal memory index after it receives programmatic confirmation of a successful file write on the local disk. By enforcing this rule, the discipline prevents the agent from polluting its own context window with failed assumptions, syntax errors, or hallucinated code blocks. This diagram shows replacing basic while loops with typed state machines to control the agent's state. Shifting to waiting approval, a lock icon represents a mandatory handoff to human oversight. During verifying, the agent programmatically proves execution success against the initial plan before closing the loop. Standard LLM wrappers consistently fail at complex tasks precisely because they lack this rigid programmatic verification phase. These patterns, permission layering, context compaction, and strict verification, provide a blueprint for building high-agency agents. While specific features like unreleased daemons or AI pets are interesting, the underlying architecture provides the reliability required for production environments. As the complexity of autonomous tasks increases, the performance gap between a basic model wrapper and a dedicated orchestration harness continues to widen. True autonomy is an engineering discipline. The models provide the logic, but the harness provides the control.